All right, welcome back. So in this video, I want to use the law of Biot-Savart to calculate the magnetic field for a straight wire. Um, to do this, before I get into this too far, let's just remind ourselves of some vector properties. Remember that for in cylindrical coordinates, whatever, we had unit vectors r hat, theta hat, and z hat. So you have to kind of picture this in the x, y, z plane. Z hat goes up, so it'd be x, y, and z. So theta hat points tangent to the circle. R hat points perpendicular to the circle, and z hat points straight up. Notice then, if you work out r hat cross theta hat, that's going to be z hat. And if you work out theta hat cross z hat, that's going to be r hat. And z hat cross r hat equals theta hat. Those are the positive cross products, and if I reverse things, I get it. Make one switch, I get a minus sign. So that's going to be theta hat cross r hat equals minus z hat. Similarly, z hat cross theta hat equals minus r hat, and r hat cross z hat equals minus theta hat. All others being 0. Okay, so that's fine. So now what we want to do is evaluate the magnetic field for a long wire and see what we find. So the picture we have is something like this. We have a long wire, or actually it doesn't have to be long, but let's say it has a wire which goes to L over 2 on the top, and I have minus L over 2 on the bottom. This is in the Z direction. And then we're going to imagine that kind of we want the magnetic field here, some point along the midpoint. And we'll say this is at a point, we'll say this is at r times r hat. So it'd be r along the radial vector at or when z equals 0. So it points a point radially away from the kind of the equator or the midpoint of this wire. So what are we expecting? We're going to have a wire here. We're going to let the current flow upwards. And if you grab that wire with your thumb pointing along the wire, with your right hand, with your thumb pointing along the wire, you see that the magnetic field will point as follows. You'll have magnetic field going out of the board on one side and into the board on the other. So over here, at this point, I expect the magnetic field to be into the board. Okay, so that would be, thinking about it, if this is Z and this is R, that would be in the theta hat direction. So we expect magnetic field to lie in the theta, in the angular direction. Let's switch over. Let me show you guys a picture of what we are imagining. Okay, so here's a picture of what we are imagining. We have a wire carrying current through the center, and then we have a magnetic field lines which which encircle it. And okay. All right. Let's go through this. Now the math here is going to be a little bit tricky. This one will involve a trig sub, so I know that Kirkland will be really excited about that. So let's proceed. We have a wire carrying current I, and here's the midpoint. It's in the z direction, and we're over here at a point radially to the side. So let's just kind of work through all of our little vectors. If I kind of mark out a generic little segment of wire, I would say that that little segment of wire has an arc length ds vector, which is going to be dz z hat. I'd say that the position of that vector, because it's the source of the magnetic field, is going to be z hat. The observation point is going to be r times r hat. Remember, this is a polar unit vector, which means it is not constant. It points radially away from the wire. So wherever you are, it will point away from the wire, which means it depends upon the angle. And then, let's see. Well, same old thing. We're going to need to find the magnitude. So the magnitude of, oh, sorry, before we even do that, we need to find RSO. That's simply going to be RO minus RS. The magnitude of RSO is the square root of R squared plus Z squared. And then because this is a magnetic field calculation, we need to calculate ds vector cross, and I'm going to use the full vector form in the numerator. So I'm going to have RSO vector. That's going to be, well, let's think about it. So that's going to be dz z hat cross r hat minus z hat. Now this is, I'm aided a little bit because z hat cross z hat is 0. So only z hat cross r hat appears. And if you look at our list here, z hat cross r hat gives me a plus theta hat result. That's good. That's what we expected. So this simply gives me r dz times theta hat. The other term cancels. So pulling it together now for my magnetic field calculation, I get that the magnetic field at this point along the midpoint is mu naught I over 4 pi times the integral of ds cross RSO. So that's going to be r dz theta hat divided by RSO to the third power. Now, the reason I had the third power is because I was using this, I'm using this form of Biot-Savart's integral equation, not the one with the unit vector. Okay, and I'm integrating over z from minus L over 2 up to L over 2. Now, theta hat is not constant. It changes with theta, but it does not care about z. So in fact, as far as doing the z integral, r and theta are constants, and I can pull them out. So this becomes mu naught I over 4 pi r theta hat times the integral dz over z squared plus r squared 3 halves from minus L over 2 to L over 2. And you can stare at that and trig sub. So let's do that. So to do this integral, we're going to make a little triangle. And I always put the variable that I'm integrating with here opposite the angle theta. I have r here, and on the hypotenuse I get z squared plus r squared. And then I can say that tan theta is z over r, so that secant squared theta d theta equals dz over r. And I can also say that cosine of theta is equals r over the square root of r squared plus z squared. If I turn that around, it means that 1 over the square root of z squared plus r squared to the third power must equal cosine of theta cubed divided by r cubed. So solving this for dz and using this last result, I plug it all in, and the integral becomes the integral of r secant squared theta d theta divided by r cubed times cosine cubed theta. That's nothing other than the integral of 1 over r squared, and then I get a cosine of theta d theta, which is going to evaluate to 1 over r squared times sine theta, and I have to evaluate it between my limits of integration. I go back to my triangle though, and I see that sine theta is nothing other than z over r. So I can write that as 1 over, or sorry, z over the square root of z squared plus r squared. So I can write that as z over the square root of z squared plus r squared. And I have to evaluate it between z equals minus L over 2 and L over 2. Whew, home stretch. You'll notice though that the upper and lower limits just double up and they work together. So this integral gives me a 1 over r squared times this in the form I want ultimately. I'm going to write this as 2 times L over 2 to the square root of L over 2 plus r squared. The 2 out front, it just comes from the doubling effect at the upper and lower limits, so how they work together. And then I'm going to simplify this maybe just a tiny bit and write this as 2 over r squared times L over, bring the 2 on the inside, and that becomes the square root of L squared plus 2R squared. Just rewriting that a little bit. Okay, so I'm going to take this answer and then plug that in to the previous expression to find my magnetic field. So when I pull it all together, I get that the magnetic field for the wire of finite length is mu naught I theta hat, this is all from out front, over 4 pi, and if you're keeping track of factors of r, we have a 1 over r squared here, and we had a r up in the numerator, so the net result is a 2 over r, and then I have this other stuff, which is L over square root of L squared plus 2R squared. Cleaning these up a little bit gets me right where I want. This equals mu naught I theta hat over 2 pi times L over the square root of L squared plus 2R squared. Now, if L is much, much bigger than R, then you can basically ignore this piece right here. And in that limit, this ratio just becomes 1. So we get the magnet, that would become an infinite wire. And we see that that is mu naught I theta hat over 2 pi. Oh, I lost my factor of R in there, 2 pi R. So that's an important result that we will see again later on. And in that limit, it becomes independent of the length along the wire, kind of suggesting that it becomes, in fact, uniform along the wire, and that is true. Okay, there you go. So that is our first example for the magnetic field due to a wire. We've calculated it for both finite and infinite wires. In the next video, I'm going to calculate the magnetic field due to a circular loop of current.